See, I started with that. I was writing, and I was like, flipping it to the eraser, and it flung out of my hand. I swear, with being the power of the I just can't do anything today. So, like, with this semester, like, I was like, glitch out. It's a little long out of my. I almost thought it took me for a second. That's how far it went. I had to go and talk. And like, I was like,
all right, class, questions about the homework? Any questions? Yes?
Workout 6.28.
628? All right. Problem 6, can you tell me what it is?
Assume distilled water sigma equals 10 to the -4 Siemens per meter. Epsilon relative equals 81. Mu relative equals 1. Fills the region C is greater than 0. At the surface we have E of 0t is equal to 8 cosine.
All right, let me do it this way. Class, I want you to understand what he's trying to say in this problem. He's saying right at the surface of distilled water, but into the surface underwater. In other words, it's not in air, or else if it was, when it came down, it would reflect. You all follow me on this? We'll get into it. He says just below the water surface. He's going to define the field, and he wants to know what the field is versus position or depth. Follow me on this? All right, so what's the field value? What's that again?
8 cosine 2 pi times 10 to the 8 t. It's in the ax direction.
Okay, is it propagating in the z direction?
It's in the ax direction.
No, that's the orientation of the field. Is the z direction the direction given as into the water?
Yeah, fills the region z is greater than 0.
All right, really, what he's trying to say is this would be positive z. It looks a little odd to everybody, I'm sure. I'll find a good marker yet. I hope. We'll work with that. So what he's trying to say is this is positive z. If you were thinking of it from another perspective, he's saying there's water over here. And here you have sigma is 10 to the -4 Siemens per meter. Epsilon relative is 81. That's about right for in the maybe 100 megahertz to 10 gigahertz range. That's about right for epsilon relative of water. He's saying mu relative is 1, right? For all those things?
Yeah.
All right. Now he says this is the positive z direction. So he's going down underwater. Think of it that way. With me? He's saying right here, this is the field right here. This would be E, but it's propagating in this direction. Y'all follow me? And what he's looking for is, he wants an equation for the electric field, I think an H field or just electric field versus that.
He wants both the E field and the H field.
All right, we're going to get them both. Now, this is one of those problems. It's a little hard in a few words to define. But he's saying right below the surface, I've got this E field. This E field is propagating in that direction, and it will decay like this. Do y'all follow me? It will asymptotically reduce its amplitude. How many see this right here? Do you not see it? I mean, can you see it back here? What I'm trying to tell you is it's propagating the Z direction. So the first thing you have to do is find the propagation constant, which has alpha and beta. So, you know, this is gamma. So gamma equals alpha plus j beta. And that's equal to the square root. If you've got calculators, get them out. See, help me with this one. So what is gamma equal to? Now think about it. Remember, gamma is a complex propagation constant. When we calculated or created, that was what? J omega mu times sigma plus j omega epsilon. You all remember this class. You got to know this, by the way. I'm trying to be as clear as I can. You have to know this. Now, here we have sigma. We have epsilon relative, and so this epsilon right here is really going to be equal to epsilon relative epsilon naught. So it's going to be 81 times epsilon naught. Do y'all follow me on this, class? Over here, by the way, when we look at this, what's the frequency, or what's omega? Just by inspection, anyone? Can you see what I've written here? What is omega, anyone? Times? 2 pi times 10 to the 8th. You all see that? That's omega, it's the coefficient of t. So I've got that. I've got mu is just mu 0 because mu relative is 1. Do you all with me, class? So could you give me the values for this? Because I don't know what it is. And give it to me in real and imaginary. Go ahead and do it. Believe me, mistakes are made right here. I promise you. This simple calculation, people mess up and the rest of the problem just is wrong. Don't make errors on easy things. And this is kind of a gimmick. I really mean it. But what I do with my, and when I used to use a calculator a lot, I had memory. I could enter something. So I put omega in like memory 1. Anytime I needed that, I just recall memory 1. Or whatever the values were. Anybody? You only have TIs, don't you? This should be a straightforward calculation, fairly quick. Yeah. I really do this. I'd have mu naught in a memory cell. I'd have epsilon naught in a memory cell, C in a memory cell. So I could just recall it and use it, and I wouldn't have to keep typing it in. That's what I used to do with an HP, but I don't know with TIs. You have memory, don't you? You can store. That's a smart thing. I've heard of people storing entire formulas and stuff in circuits and just recalling the formula and then putting in values for whatever it is, voltage, current, or something. So what do you get for this? You're taking that long. Maybe a lot of people aren't doing it, but it shouldn't take very long. You got omega is defined as 2 pi times 10 to the 8th. You can just store that. Then you have mu is mu naught, right? 4 pi times 10 to the minus 7. Sigma is 10 to the minus 4. Epsilon naught is 81. Anybody at all? It's taking longer than it should. You got it? Anyone? Was this the problem? This right here? Yeah. What'd you get? Don't worry about the answers, just tell me what you got. For alpha, J beta. Go ahead. Anyway.
0.0188.
0.0188 plus J?
J2095.
2.095?
2.095.
0.95. Anybody else? Anybody? Confirm or deny? Not bad. Say again? What? Is this right or wrong?
That's
Wrong. At least it's average that.
Is epsilon relative to 81?
Yeah.
And
If you don't, epsilon naught, most people, you should know this by now, but epsilon naught is about 8.854 times 10 to the minus 12 farads per meter. And mu naught is 4 pi times 10 to the minus 7 henries per meter. That works. This shouldn't be that. Now, if you don't have epsilon naught, mu naught, and C stored in your calculator, this is kind of a smart thing to do. And I would store those values so you can recall them quickly. Yeah.
I got
What did you get?
it. For the real part, I got 0.00209.
0.00209?
Yeah, and then the imaginary 18.86.
Anybody else? You got that?
yeah, that's what I got.
You got that, everyone? Please know how to do these calculations efficiently. I'm giving you a tip. This will save you loads of time on the final. Because this is stuff that can suck time if you're not familiar with how to do it efficiently. Now, is that right or not, Gabriel? Is that right in the book or not? I don't know, solutions are there.
It's correct in the solution.
It is? Okay, we'll assume it is. Now, once we have that, we have to define the E field. I'm going to do it first in the time domain, then in the phasor domain. With me? I'm going to do it over here too. So, it's propagating in the z direction, it's a plane wave, and it's in a lossy material. Therefore, the E field itself will be E naught, and he gives you it as a magnitude of 8. It'll have the cosine of omega t. I'm just going to leave it as omega t because I've defined omega as 2 pi times 10 to the 8. It's propagating in the z direction, positive z. Hear me, everyone? So it's minus beta z. Y'all hear me? What is beta? Just look there. Can you all see this, class? This is beta. It is the coefficient of the imaginary component of the propagation constant. Guys, can you see it back there? Can you see what I'm writing and you understand what I'm saying? Right? You got me on this one? All right, so that's beta. So beta would be, if I put it down there, 18.86 z. It is in the AZ, this is in the AX direction, but there's one other thing I have to include. It's the exponential decay. I'm going to put it in front so you can see it matches his form. It would be 8, and then it would be e to the minus alpha z. Here, alpha would be this. I probably should have put beta there too, but alpha would be 0.002209. Okay, now that would be the form for the E field. Does he have that form in the time domain, by the way? Anyone? Can you look at the answers? Because we're going to go phasor. I don't know if he gave the phasor or time. You all understand this is a time domain form. This would be the observable electric field that you could actually measure theoretically. You got that? Is that right? Okay. Now we're going to go to the phasor domain for the electric field. Now, class, this is one thing I really... Yes, sir. Go ahead, Jeremiah.
What does the Z mean?
Z is the direction of propagation right here, right? It's propagating in a positive Z direction. By definition, he said positive Z is into the water. When I think of water, I think of going right, which is usually minus Z. But I didn't define the coordinates for this propagation. You good with that? Gabriel? Everybody? Now, we're going to go right to the phasor domain. Now, this is where people mess up. I'm telling you, there's just subtleties they don't feel like spending much time on. For the phasor domain, remember, the 8 stays there. That's just the magnitude. The e to the minus alpha z comes out. Y'all with me? Now, there is no omega in the phasor domain. Do y'all hear me on this? There is no cosine of omega t or e to the j omega t. In the phasor domain, that's suppressed. The next thing we get is e to the minus j beta z. And it is in the AX direction. Now, that's the phasor form of the E field. Can y'all hear me on this one and see this? Does everybody understand what I'm trying to get at? It's really that simple. And the relationship between the phasor domain and the observable time domain is simply this. If you wanted the electric field in, say, ZT, this is observable, that's simply the real part of the phasor form times e to the j omega t. Now this works if it is at a constant frequency. You can't do phasor analysis if you have something that doesn't have a defined frequency. In other words, if it has something that's, say, a time domain pulse of short duration, it doesn't work. Do y'all follow me, class? So this would be phasor and it would be temporal domain. With me? Or phasor and time domain. Everybody? Now, if I have these two fields and I want to get the H field, there's one other thing I need. I'm going to do the equations. Let me erase this. We've got the E field down here. I'm assuming we have alpha and beta recorded somewhere. So now, the one thing I need, once I have alpha and beta, I also need eta, right? Let's get eta together. Y'all with me? What is that called, by the way? Intrinsic impedance, right? Y'all with me? Intrinsic impedance. It's the square root of j omega mu over sigma plus j omega epsilon. Now, if you use this equation, you can't go wrong. We can say if it's a lossless media, then it's just square root of mu over epsilon, because sigma is 0. And if it's a very good conductor, it would just be j omega mu over sigma. But this works all the time, no matter what the values of epsilon relative are, mu relative, or sigma. Got that? This one is a guaranteed winner. Now, what is the value for R? Really, for the things that we have to work with. It's what? J and omega is 2 pi times 10 to the 8th, right? So it's j omega mu. Mu is just mu 0 over sigma. It's 10 to the minus 4th, right? Plus, and it's going to be j omega, and that's omega. Mu relative is 81, and epsilon naught. So what do you get? And give that to me in magnitude and angle, please. Work at it. Please just try this on a calculator. A lot of people just don't want to do it. Oh, I got this. I promise you, on exams, people make the dumbest mistakes doing the simplest calculations. I promise you. If you can discipline yourself to force yourself to do these repeatedly and get the same answer, you will thank me. If you only knew how many people mess this up and they come to go, oh, I just made a mistake there. Well, why did you make a mistake? Well, I don't know. And I promise you, I don't know how you calculate this, but if you can store epsilon naught, mu naught, and C, the velocity of light, in memories, and just recall them, you're going to thank me, because that will save you so much punching in. That 8.854 e to the minus 12 stuff it drives me nuts after. Do we play tonight? Basketball? What time? 8:30 or 7? What's that? That's too late for me to go.
So you wanted polar?
Yeah, magnitude and angle.
41.859.
41.859.
E to the 0.006.
Is that radians or degrees?
That is radians.
Can you give it to me in degrees?
Yeah. Actually, no, that's degrees.
Say that again.
0.006.
0.006
That's what I got.
degrees. Anybody else? I'm just asking for confirmation. You got that? All right, now we've got that, right? That's almost 0, right? That's about, personally, I'd ignore it. It looks like at an angle of 0 degrees. Y'all follow me, class? Okay, so if that's the case, now what I'm going to do is get the H field. And remember the simple trick I showed you for propagating waves, there are 2 equations. One is if you wanted H and you had E for propagating plane waves, you can simply say 1 over eta, the intrinsic impedance, A rho unit vector in the direction of propagation, crossed into E, to get the H field, or to get the E field, this is in Whitmer's book, minus eta, unit vector in direction of propagation, crossed into H. Do you remember these 2 equations? How many do? These will save you huge amounts of time. No curls necessary. No integration in time, like in chapter 5. Just straightforward couple of cross products and you're done. Y'all hear me on this one, class? So let's do this. We have the E field in the phasor domain. Right here. We want the H field in phasor in time. We have eta, right? We have the direction of propagation. Let me do it over here. So I'll do this last part right here. So what's the unit vector in the direction of propagation? Class? For this problem. Yeah, it's AZ. That's the direction the wave is traveling. Y'all follow me? How many see this right here? And understand why? Y'all see it? I want to make sure. you're not, I'm making sure. If you don't, just tell me and I'll try to clarify. How do you find the direction of propagation using either time or phase or domain? What's the one key thing? Anybody? What do you look for? Say in this time domain. You look for what? The spatial variable inside this cosine argument, right? And then you look at the coefficient of the spatial variable. That's beta, isn't it, class? And if it is minus, then that wave is going in the plus direction that has to do with the coordinate, right? Okay. If it's plus, it's going in the minus. Do you all remember that? Now, if it's over here, if it's phasor, you just look at the coefficient of the spatial variable. And this is going to have the imaginary component, the beta. And if it's a minus there, it's going in the positive z direction. You all with me? If it's plus, negative z. With me, class? All right, so that means this is in the positive AZ. Now, what is the H field in the phasor domain then? 1 over eta. I'm going to forget about that angle, so I'm going to just put 1 over 41.859, right? Then I have the unit vector and direction of propagation, AZ, crossed into the E field, which is 8 e to the minus, I'm just going to leave it as alpha z, e to the minus j beta z ax. So therefore, what's the H field going to be in the phasor domain? First, let's do it this way. Take 8 over 41.859. Can somebody give that to me? 8 over 40, about 1/5, is that right? 0.19. 0.19 approximately. Then we have e to the minus alpha z, e to the minus j beta z. Then we have az crossed ax is what? Az crossed ax is a y, isn't it, class? A y? Now I ignored that angle. You see, if that's right, 0.006 degrees, it's about 0.00000 degrees. It's 0 to me. Y'all, we're engineers now. We're not going to split hairs and out. All right, and that would be amps per meter, right? Now, how do you get H in the time domain? Technically, what do? Just take a moment there. The real part of the phasor H times e to the j omega t, right? Y'all hear me? What does that really do? It creates a cosine of omega t minus beta z, doesn't it? And the e to the minus alpha z comes out front. So this is going to be equal to 0.19 e to the minus alpha z. That's up in front. Then it's going to be cosine of omega t, which omega is right there, minus beta z. Beta we know. And it's going to be in the AY direction, and that's amps per meter. So that's H, is that right? For time or phase. It is?
Yes.
Okay, if that's right, does he ask for power?
Yeah, he asked for that. Yeah.
We're going to get power next. Remember, that was one of the parts of the lecture last night. So how do you get power? Well, I gave you the general formula for a plane wave propagation at the end. I'm going to do something now. Now, when you're an electrical and computer engineer or a physicist or material science, anybody that's working with materials where you have power flow, you have to have very precise ways to defining the power density that's flowing, the energy density that's stored, and the power that's dissipated. There's three things. The flowing power density, the amount of power that's actually going to be dissipated, that would be watts per meter cubed. And then you want to talk about the energy densities stored, both magnetic and electric. So when you talk about average power flow, this is his term in the book. I prefer SAV because it's in the literature, it's used all the time. That's called, what's the name of that vector? The pointing vector, right? Pointing, not spelled that way, but pointing vector is what it's called. And it's equal to technically what? 1/2 the real part of E cross H conjugated, right? These are phasors. That's the definition. Very similar to V times I conjugate in just general power flow for your power course. Do y'all remember that? But for us, once you go ahead for a plane wave propagating, this works all the time, by the way, but for a plane wave propagation, it's 1/2 magnitude of the E field squared, E naught squared, over magnitude of eta, that's the intrinsic impedance. It's e to the minus 2 alpha z. Now, I proved this last time. Do y'all remember me doing this? How many do? And there's one other term. It's the cosine of the angle associated with the intrinsic impedance. In our case, it's in the AZ direction, and it's watts per meter squared. So I want to make sure you understand this is power density flowing. Really power density, but it's flowing or propagating. Y'all with me? I'm going to show you 2 other things now. Now, in his book, we'll get the answer to this one right now. So if we take a look at this, let's get the power density flowing for his problem, okay? So this power flow, the average power flow, would be 1/2. The E field, I think, was 8, wasn't it, class? Was that 8 volts per meter? The coefficient? All right, so it's going to be times 8 squared over the magnitude of eta. Was that 41 point something? Can you tell me what it was? So it's over 41.9. Because the angle is about 0, I'm not even going to worry about it. Because the cosine of 0 is 1. Now it's times e to the minus 2 alpha, and alpha, I forgot what it was. I'm just going to put 2 alpha z here, whatever that is. Y'all with me? And this would be in the a z direction. There should be a cosine of that angle, but the angle is 0, cosine of 0 is 1. This would be watts per meter squared. What is that going to be, actually? So you got 64 over 2, 32 over 41.9. A little less than, what, 0.8, 0.75, something like that? I don't know. Can anybody tell me that? Just pick, what is it?
0.76.
0.76. E to the minus 2 alpha z, AZ, watts per meter squared. Does that agree with this book? With me? Now that's the power density flow. I want to put forth a couple other things. Whenever you have an electric field present in a media that it's got conductivity, you're going to have current flowing. Whenever you have current flowing, you have power being dissipated. You know, with a resistor, anytime you have current in a resistor, there's a dissipation of power. The power that's there is going to be, if it's DC, it's I squared R. Do you all remember that? If it would be AC and you're taking the actually average power, it's 1/2 I squared times R. Do you all remember? That's power that's dissipated. It means if it's electrical current flowing, it's usually turned into heat, thermal heat. It could be turned into light. It could be turned into other forms, but it's actually dissipated or changes the actual form of the energy or power. So over here, this is power density. When we talk about power dissipated, I'm going to call it P dissipated here. This is power that's dissipated per meter cubed. This is equal to sigma, which is the conductivity of the media, and it's going to be times the actual magnitude of the E field squared. Now that's in his book. Let me see if I can find that for you. Can't be.
That's supposedly in here. It says it's on 181. Oh. Okay, so he shows us. It doesn't show it the way I'd like him to show it, but it's on page 181, equation 3.94. But if you get the integral away from that, you're going to see the power dissipated is sigma E squared. And I'm trying to figure out why he doesn't break that out single. It's probably in there somewhere else, but just note this.
This is the power dissipated. The units are watts per meter cubed. Now, another way to put this is simply going to be it's equal to J dot E. That's the power dissipated. If you think about power dissipated is what? V times I in a resistor, right? Voltage times current. Same thing here. J is amps per meter squared. E is volts per meter. So you have volt amps per meter cubed or watts per meter cubed. That's dissipated. That's the amount of power that's just lost. Then you're going to have actual electric and magnetic energy density. The electrostatic energy density is going to be equal to 1/2 epsilon times magnitude of E squared. The units of this are joules per meter cubed. And then the magnetic energy density is going to be 1/2 mu magnitude of H squared. But that also has units of joules per meter cubed. I'm putting this down there so you at least have an appreciation for what each one of these mean. This is power flowing, power density. It's very important to know how much power density is going to be on a target with radar, antennas, and things like that. The power density times the size or aperture of the antenna, it tells you how much power is actually received by that antenna. And this is a real important quantity. This tells you, if you know a region of space and you're transmitting in it, this tells you how much power is being dissipated per meter cubed. Now what you can do is figure out how fast the region heats up. If you know the I don't want to go too far afield on this, but you know what the specific heat is from chemistry and stuff like this? All right, if you have that, you can figure out how fast the region will heat up. Then you go through phase changes. A lot of that is later on in your careers as engineers, but you have to at least have an understanding what these terms mean. This tells you how fast the energy is, or the power is going to be dissipated within a region. This is how much energy is stored. Now in a capacitor, for instance, you charge up the capacitor, nothing's propagated. There's electric field, a static electric field around there and between the dielectric that exists. If you take and find the electric field at all points around that capacitor, square it, and multiply it by 1/2 epsilon, you get the density, or the energy density. And if you integrated it over the region the field exists, you get the total energy in a capacitor. And that would be equal to 1/2 CV squared, because that is the way we think about the lumped elements storing energy, right? Capacitor's energy is 1/2 CV squared. Here, this gives you the energy density in the field from a magnetic field. It doesn't have to be static, but if you have an inductor, you have current through an inductor, it creates an H field. The H field is, if there's no change in current, it's static, right? And if you know what the H field is, take it and square it, multiply by 1/2 mu, now you get the magnetic energy density of the field. And if you integrated that over all space where the field existed, you would get the total magnetic energy in the inductor. And remember, we did this to calculate inductance. That was equal to 1/2 Li squared, right? We could find L from that. We could find C from the other one. But these are the important things to understand with power and energy, especially power dissipation, power flow. Follow me? Y'all with me on this? You may not like it, but this is how you're going to make your livelihood understanding this stuff. If you're an electrical and computer engineer, this is your bread and butter, understanding the underpinning physics for all the stuff that we do. A lot of times it sort of gets lost. I mean, you have what? You're having digital, right? When you talk about inverters and, memory and all that stuff, you're really not thinking about the solid state physics. You're thinking about simple transitions from state transitions and stuff. But
ultimately, it's the physics that governs all that, fundamental physics. Okay. Another question, I spent some time on this one, but I thought it was important, because that's a good problem, by the way. It really showcases everything. The different field forms and the power density. You got another one for me?
Yeah, we can go ahead and do 6.30.
Sure, we'll do 60. I think this is the best way to do this, just work some problems, because how many tried the problems? I mean, if you haven't, I understand, you got a lot to do, but it really helps when you keep up. I know you can cram, but it's not, I think in the long run it'll hurt you. Our final is Wednesday, and it is at 10:30 or? Y'all hear that, class? Final, Wednesday, 10:30. If you don't know how to find out where the final exam is, or anything about it, if you're new here, type in Auburn University final exam schedule, and poof, it should come up. I've been told a lot of you have sequential finals Tuesday, Wednesday, and Thursday. As long as you don't have two or more on the same, 3 or more on the same day, it's fine. When you have 2, it gets a little tough, but 3, it's really rough. All right, 6:30, did you say?
Yes.
All right, what's this one?
A 200 megahertz uniform plane wave incident on a thick copper slab imparts a 1 millivolt per meter amplitude at the surface.
Okay, hold on. You got an electric field. This propagating in, this is copper, right?
Yes.
The copper has a conductivity of 5.8 times 10 to the 7th. It's Siemens per meter. A Siemens is 1 over ohms. And so the field inside the surface of the copper is what strength here?
Copper slab imparts a 1 millivolt per meter amplitude at the surface.
All right, so that's enough. Go ahead.
And the question is, how much power passes through a square meter at the surface? And the other question is, how much power passes through a square meter area 10 micrometers beneath the surface?
All right, now if you think about this right here, if you can imagine in your head, if you have a region here that's 1 meter squared, but it's planar to this wave. You want to know how much power passes through that. Y'all with me? Right at the surface. Can everybody follow me on this, class? So we're going to first find the power density at the surface. Y'all with me? But this is in the copper, remember that. Follow me? So if we're in the copper, power density is what? I mean, the power flow, power density. P is equal to what? 1/2, right? Magnitude of the E field squared over eta. Now, does he say that's the field in the copper, by the way, or is it outside?
So the parts A.
Okay, so it's inside the copper. All right. It's 1/2. Let me blow that up a little. And this is the actual density of the power flow. So P Av is 1/2 magnitude of the E field squared over magnitude of eta. Then it's going to be e to the minus 2 alpha z right there. And it's going to be times the cosine of the angle theta eta in the AZ direction. I'm going to assume this is z, just for lack of a better assumption. So I'm going to assume this is going in the z direction. Y'all with me, class? So let's go ahead and do this. We need a few things. We got 200 megahertz, so the first thing we need, I'm going to put omega down here as 2 pi times f. So that's really 400 pi times 10 to the 6. That's going to be omega. Now, the next thing we need is going to be eta. Well, we'll get gamma. Gamma is equal to alpha plus j beta. Here, that's going to be the square root of j omega mu times sigma plus j omega epsilon. That's the formal way to do it, right? I want to make a comment here. Can you all see what I've wrote there? Is it too small? Can you see it in the back? Now, comment. Copper. Copper, good, bad, or indifferent conductor. Very good conductor. What do we do with J omega in that equation? Remove it. What do you know? For a very good conductor, alpha is beta. Do you remember me telling you this? As a matter of fact, you can say alpha, you can prove this, equal beta equal square root of pi f mu sigma. You can go ahead and take a look at your notes. If you do this, this is exactly what you'll get. You're going to get J is 1 plus J over square root of 2. Omega is 2 pi f, so when you take the square root of 2, inside there you get pi f mu sigma. This is what you get. Can somebody give me that? Pi times 200 megahertz times mu 0, and sigma is 5.8 times 10 to the 7. Can you follow me when I'm doing this? We're going to get the power density in 1 second. I want to show you how to make sure you get these calculations done. Anybody confirm that? 1.41? Anyway. Did you get it? How many got it? How many did it? Just do it for me. If you got something different, tell me. I need to know. It's pi f mu sigma. Pi times 200 megahertz times 4 pi times 10 to the minus 7 times 5.8 times 10 to the 7. I don't know what it is. Let's pull up. Yeah.
I got it. 5.8 times 10 to the 2nd. 5.8 times 10.
What did you get?
214 milli. Oh, it's 400 because you have 2 pi times frequency.
I got 21399.7.
That's what I got.
Whoa. 2, 1, what?
21399.7.58.
All right.
214,000.
Yeah.
If you round up those lines, it's just 214,000.
Yes.
Is that right?
Yeah,
That's what I got.
That's a lot. Okay. So this is a big number. All right. We're going to assume I'm going with this one. I don't know if it's true. Is that right or not?
yeah.
It is
That's
good.
right.
All right. Next, let's get eta because we're going to need eta right there, right? Eta is going to be equal. Is it a good conductor?
Yes.
Yeah. So it's J omega mu over sigma, right? So if you just give me the square root of omega mu over sigma, it will be at an angle of 45 degrees. Trust me on that one. So what is the square root of omega mu over sigma? Do the calculations, it helps. Yeah, because square root of j, what is j? 1 at an angle of 90, right? The square root of j is just e to the j 45 degrees. I took it outside, that way I don't have to mess with it. Say again? So eta is 5.22 e to the j 45 degrees. Is that right? That would be ohms. Class? Milliohms? Milli. Oh, okay, that's an important fact. So it's really, let me do it this way. So it's 5.22 times 10 to the minus third e to the j 45 degrees ohms. So it's milliohms. All right, so it'd be 5.22 milliohms. But I want to clear that. Y'all with me on this? Now, this is real important. Now you're coming up here with the power density. This is in watts per meter squared, by the way. All right, so for this one, we're going to get the average power density at the surface equal to
1/2. The E field was 1 millivolt, so it's 10 to the minus 3 squared divided by magnitude of eta. I'm going to put it in here, 5.22 times 10 to the minus 3rd. Then I need to go ahead and I'm going to leave the e to the minus 2 alpha z here. We don't need to worry about that yet. The cosine of 45 degrees. So this angle right here would be 45 degrees for a good conductor. Does everybody see that? The cosine, the angle associated with the intrinsic impedance is 45 degrees. The cosine of that angle goes into this formula. Cosine of 45 is 1 over square root of 2. So we divide this by square root of 2. Can you give me the coefficient there? Forget the e to the minus 2 alpha z. Just tell me what that is. So you get 10 to the minus 6 over 2 times 5.22 times 10 to the minus 3rd. Square root of 2. Oh, that's 10 to the minus 6. 10 2. About 10 to the minus 4, somewhere in there. What'd you get? Anybody? It's got to be real close to that.
The solution was 10 to the minus 3.
Well, look, this is 10 to the minus 3 squared. That's 10 to the minus 6. It's divided by about 10 to the minus 2. So, isn't it 10 to the minus 4? Is it 10 to the minus 3? Hey, what did you get?
I got 6.7 minus 5, 10 to minus 5.
Great. Am I doing this right? So if I have 1/2, 10 to the minus 3rd squared is 10 to the minus 6, right? Then you got 5.22. Maybe I am wrong. 10 to the minus 3 here. That's about 10 to the minus 2 right there. Then I got square root of 2, right? So what do you get for that? So I got what?
I get 6.7 times 10 to the minus 5.
Is that 10 minus 5? I'll go with it for now.
Oh,
What? Say,
A few of us got, I got the same.
6.7 minus 5.
all right, we're going to go with that. That's the average power flow at the surface, right? He wants to know how much power flow is in 1 meter squared. Just multiply it by 1 meter squared. Is that the answer? For the first one.
No, it doesn't have the square root of his answer.
Well, look, you see this? You got to have the cosine of the angle. The cosine of 45 is 1 over square root of 2. He may have forgotten. You all with me on this, class? It has to have the cosine of 45 there. And that's 1 over square root of 2. I'm really out of my mind. You all right? Everybody with me on this? This should be the right, is that right there? Or not?
That's the answer I got, but it's different in the book.
All right, he forgot the square root of 2. Look, he did, see how that appears there? Did he have this formula in his book? In the solution.
He just has the first half, he doesn't have the cosine.
All right, that's the problem. The cosine has to be there. He probably omitted it by accident. Put it in, because that's important. So if that is the power density, if you multiply that by 1 meter squared, that is how much flow is flowing through 1 meter squared. With me? Now, I'm out of time, but if you go down, how far do you say down?
Square meter area of 10 micrometers
But-
beneath the surface.
10 micrometers,
Yeah,
that's the distance.
for the second part, yeah.
All right, listen, the only thing you have to do, see this equation I did? Is put in z here is 10 micrometers, which is 10 to the minus 50. You got me on that? You put that in there, this coefficient will reduce that value by e to the minus 2 alpha times that z. But it's still flowing through 1 meter squared. You all follow me? All right, for Friday, last quiz. Here we go. It's going to be on the stuff we covered today and on Monday. So it's going to have to do with power flow, phasor form of E and H, E and H in the phase are formed for plane waves. Therefore, E or H is equal to 1 over eta, rho, crossed into the E field. E is minus eta, and it's going to be a rho crossed into the H field. Remember the power density, and don't forget their cosine. Got me? I'll see you Friday. Sorry I didn't have more time, but that energy density stuff I put up there and power density is important too.